We are on to everyone's favorite topic, inverse trigonometric functions. Now, let's start with sine x, and before we talk about its inverse, let's take a look at the graph of the actual sine function. Here it is. Recall that in order to have an inverse, a function must pass a horizontal line test, which means that if I draw a horizontal line, it can only cross the graph at most once. Clearly, that's not the case here because every horizontal line will cross the graph multiple times, and in fact, if we continue, it's clear that it will cross it infinitely many times. So as is, the sine function has no inverse. One way to solve this problem is to restrict the domain. So not consider the entire curve between negative infinity and infinity, but rather take a piece of it that will pass the horizontal line test. For example, we can restrict our attention to the piece of the curve right here. So if all I'm looking at is this piece of the sine function, then it will have an inverse because this part does pass a horizontal line test. Now, of course, I could have chosen, for example, this piece and it would have also passed a horizontal line test, or I could have chosen this piece or any other piece. It is simply a convention to choose the restricted domain for the sine to be between negative pi over 2 and pi over 2. Just like other conventions, it is there just so that when we're talking about the inverse sine, we have the exact same things in mind. Okay, so let me note here, this is just a convention, but an important one to remember, so we're all talking about the same thing. This is once again the graph of the sine function on this piece between negative pi over 2 and pi over 2. And in order to draw the inverse of it, let's remember that the inverse is the graph reflected in the line y equals x. So I can draw the line y equals x, the perfect diagonal here, and I can reflect the graph of sine in this line in order to produce the graph of the inverse sine. Okay, so the easiest way to think about it is if you drew the sine graph here in wet ink, and then you folded the page along this line. So where would the trace appear? We notice that it will mimic the shape of the graph here, but will look into the opposite direction. Okay, now my sketch is obviously not going to be perfect, but it's going to be a pretty good approximation of it. So this is the sine inverse. Okay, this is another very important convention in this case. The inverse of sine of x is denoted by sine to the negative 1 of x or arcsine of x. Okay, so it's incredibly important to realize that sine to the negative 1 of x is not a reciprocal of sine, so not a cosecant. This minus 1 does not represent the power, it represents the inverse of sine of x. Again, this is just a convention, it's a shorthand of writing it. I personally prefer to write arcsine in order to avoid this potential confusion, but most of the books and lots of instructors use sine inverse as the notation for the inverse of sine. The other interesting thing to note here, for example, is what is the domain of the original and the range of the original function. The domain represents all the possible x values, and what are the x values here? Well, I can plug any number in as the angle, and so the domain are all real numbers, and they're all of the angle measures. Whereas the range will be all the possible y values, and they are numbers between negative 1 and 1. So the range between negative 1 and 1. For the inverse case, this will all flip. So the very first thing we can think about in terms of properties of the inverse sine is the fact that what is put in inside is a number, and what comes out as the output is the angle measure. So the exact opposite of what's happening in the sine. When you're computing with sine, what you put in is the angle measure, and what you get out is a number in the range between negative 1 and 1. For the sine inverse, what I put in is the number in that range, and what I compute as the output is the actual angle. So what are some of the other properties that we can notice of the sine inverse? So first of all, let's talk about the domain and the range. You can remember from the discussions of inverse functions in precalculus that the domain and range for the inverse functions are the opposite of the domain and range of your original function. But we can also take a look at this graph here to further solidify that point. For example, we can also mark more values on this graph. We know that the sine curve goes between negative pi by 2 and pi by 2, and in terms of y values, it goes from 1 to negative 1 over here, which means that the domain for the inverse sine will be the outputs of the sine function, which will all lie in the range between negative 1 and 1. So the domain is from negative 1 to 1. The range of the inverse function are all the possible outputs that it can produce, so along the y-axis, and we can see here that it's going to be everything from negative pi by 2 to pi by 2. So this is going to be the range. And again, this is consistent with the restricted domain of the sine function that we had to take because of the horizontal line test, as well as the range of the sine values. What is really important to recognize is the connection between the inverse sine function and the sine function itself, which can be represented in the following relationship. If I have sine inverse of x equals y, this is equivalent to saying that sine of y is equal to x. If this is the angle you put into the sine to get the value of x, then the sine inverse of that value of x will be that angle y. And in fact, it's probably best to think of the inverse sine of x as the number, as it is, in the range between negative pi by 2 and pi by 2, whose sine is x. Okay, so it's not just a button on your calculator. This is the true meaning of sine inverse. Now, keeping this definition in mind, let's take a look at a couple of various evaluations that we can perform. So, sine inverse of 0. That means that I have to think of an angle whose sine value is 0. Okay, remembering our lovely unit circle, I can remember that the sine corresponds to the y values, which means that the sine of 0 will be 0. So here I can have a 0. Now notice that I can also remember that sine of, for example, 2 pi is 0. However, my range of the inverse sine is restricted to be between negative pi over 2 and pi over 2. So I'm looking for a unique angle measure here, right? So this range here guarantees unique appearance of the angle measure. This will produce some slightly bigger analysis further down. Like, for example, let's take a look at the next question here. So I have to think of what sine of what angle will give me a value of 1. So sine of what angle equals to 1. And again, let's recall the unit circle. Let me just draw a quick sketch of a unit circle here. Sine is the y coordinate. So out of what points on the circle do I have y coordinate equal to 1? Well, it's this point right here. And in fact, it's the only one. So it's pi over 2. So I can say that the sine inverse of 1 is pi over 2. This is the unique solution in this range. However, of course, if I have to think of sine of what angle produces 1 as the answer to this question will be pi over 2 plus 2k pi. So plus however many rotations I choose to put on top of this point. So here, and I can rotate around and land again here and around and so on. Okay, so the value of the inverse sine will be unique, but it's not the only solution to an equation like this. And this is something we have to keep in mind later on. For the next one, sine inverse of 1/2. So we have to think of what angle has sine value of 1/2. And this is one of the special triangles. So sine value is the y value, 1/2 is somewhere here. So I noticed that already, for example, I have 2 answers in the first rotation, but sine inverse being restricted to negative pi over 2 to pi over 2 will only give me answers in this region, which means that I'm only after this one particular value, which again, recalling the special triangles, will be pi over 6. Next up, we have sine inverse of 2. So I have to think of what angle do I have to compute the sine of to get the value of 2. Well, I know that this is impossible. Sine of no angle will be 2 because sine of anything is restricted to be between -1 and 1. So this is simply not possible. You also notice that the domain of the inverse sine for that reason is between -1 and 1. So the moment you see a number that is outside of that domain, you know that this is undefined or does not exist. Just for a switch of notation here again, arc sine is the same as sine inverse, and we're asked to compute arc sine of -0.9. So this is asking sine of what angle is equal to -0.9. Now this is clearly not a number that is within any kind of special triangle. The only thing I can tell from the unit circle is because it's the y-coordinate, it's got to be negative, so it's got to be an angle somewhere here. I'm going to, in this case, use a calculator in order to be able to figure out the exact value, but it turns out to be approximately -1.1 in radians, which is also approximately minus 64 degrees. Okay, so be careful also about which mode your calculator is in, radians or degrees for these types of calculations. Let's take a look at this one here, arc sine of pi. So we're asked to compute sine of what angle is equal to pi. Well, the problem is pi in itself represents an angle measure, so it's never going to be the output of sine. It's in fact going to be the input of it. So this is not even well defined at all, right? This is not what the arc sine takes in for the input. It's what sine would take for the input. So this is again emphasizing the fact that what goes into sine has to be the angle, and what it outputs has to be a number, as opposed to arc sine that takes in the number as the input and outputs, where possible, an angle measure as the output. For other inverse functions, we can follow the same type of development as we did for sine. So take a look at cosine here. Once again, we have a problem that it does not pass a horizontal line test, and therefore we have to introduce a restriction to the domain for it to pass the horizontal line test. And once again, we actually have quite a few choices. We can restrict it to any bit of a curve that looks like one piece that will pass a horizontal line test, and by convention, that piece is chosen to be between 0 and pi. So that piece will be the function from here to here. Okay, so this is copied again over on this side. This is the graph of cosine of x, and let's label it goes from -1 to 1. And in order to get the inverse function, I'm going to draw the y equals x line that we need to reflect everything in. And I'm going to reflect this graph in this line. So once again, think about drawing this in wet ink and then folding the sheet of paper over this line. All the points are going to acquire their opposites. So this point of 1 will appear here, and it will turn, and the points that are on the diagonal will actually stay there. And then we can also sketch to see where this point occurs. It will be the point somewhere along here, and I can connect the two. If you just flip your page a little bit sideways, you should be able to connect the two in the similar curve to the cosine, actually going through pi by 2. So actually going through this point as my curve did before. There we go. So again, if you rotate your page 90 degrees, you will be able to slightly better actually draw a more smooth curve. So this is cosine inverse of x. Let's list some of the properties in the same way we've listed properties of the inverse sine. For the domain and range, for the domain, we can once again see that they will flip. So the domain for this will be between -1 for this and up to 1, consisting of the values that the original cosine function would have produced as the output, and the range we will take our restricted from 0 to pi as the convention. And again, we're taking this so this produces a unique angle measurement. Once again, let's think about cosine inverse of x as the number in the corresponding range, so in 0 pi, whose cosine is actually x. Writing this in terms of the functions, if I am saying that cosine inverse of x is y, this is equivalent to saying that cosine of y is x. So notice how my input and output switch places here. This is saying that y is the angle measure and x is the number. Inverse cosine says that you are given the number and you produce the angle measure whose cosine would have been equal to that number. The exact same logic can be applied to further develop inverse of tangent and all of the other trigonometric functions. We will only take a look at tangent because, again, the analysis and logic will stay the same. Once again, the situation is the same for tangent. If I draw a horizontal line, it does not pass the horizontal line test, so I have to reduce the tangent to just one part of its period so that the horizontal line test is passed. I can once again draw the diagonal y equals x, and I'm going to have to reflect my tangent curve in that diagonal in order to produce the inverse tan. Notice that this is the one function where I'm dealing with asymptotes that I haven't seen with sine and cosine before. And asymptotes, when reflected in y equals x, will turn out to be horizontal asymptotes, not vertical. Everything switches directions here. And then overall, my graph will flip to be something like this. So this is tan inverse of x. Okay, so notice the newly present asymptotes. The domain is then all real numbers. Notice that the output of the tangent to begin with was from negative infinity to infinity. So the domain now, all of the things that I can plug in, or all the possible values of x, are all real numbers, whereas the range is now restricted to be between negative pi over 2 and pi over 2, not including the endpoints, because those are actually our asymptotes here. Okay, let's take a look at some examples here just to get used to the notation and actually figuring out how to compute these things. Evaluate where possible. So we're here asked for unique values. Okay, so not yet solving equations that we're going to get to shortly, but unique values of these functions. The first one, cosine inverse of -1. So once again, rewriting it, that means that I have to think of the angle whose cosine is equal to -1. Whether you choose to think of the unit circle or you actually know some special angles by heart, you should have no trouble thinking of pi as the answer here. For the next one, tangent inverse of 1. So once again, that means that we need to think of the angle whose tangent is equal to 1. This one's easy because tangent is sine over cosine, so we're thinking of the angle when sine and cosine are the same, which is the angle of pi by 4. Next up, x is cosine inverse of 3, so I need to think of the angle whose cosine is 3. Now, cosine is restricted between -1 and 1, so I know that this does not exist. For the next one, tangent inverse of 3, so I need to think of the angle whose tangent is equal to 3. This, of course, is possible because tangent originally does not have restrictions on its range. It can be anything. And in fact, if I have to see tangent of what angle is 3, I know that it's this line right here that is at 3, and I'm restricted to only this piece of my tangent function, so I know I'm after this point right there, somewhere right there, which happens to be somewhere between pi by 2. Plugging this into a calculator, you will see that this is approximately 1.25 radians or 71 degrees. okay, which again seems reasonable. This will correspond to a point somewhere right here, which is pretty close to pi over 2, which would be 90. Okay, the next question asks not to compute, but rather to simply rewrite the expression using the inverse trig functions when the original expressions are given with regular trig functions. So this just is doing the exact same thing as above, but in the opposite direction. Cosine of pi over 3 equals 1/2 is the same as saying that cosine inverse of 1/2 is equal to pi over 3. Okay, so again, notice how the input and the output switch order or switch places. And here I'm now asking cosine of the number, inverse cosine of a number, 1/2, is produced by the angle of pi over 3. And moving right along, the next one will say that cosine inverse of 0.8776 is approximately equal to 1/2. Not every angle has a nice representation in terms of arc cosine or arcsine or any of the other inverse trig functions. Tan of pi over 4 is equal to 1 is the same as saying that tan inverse of 1 is pi by 4. Sine of theta equals 0.3 is the same as saying that sine inverse of 0.3 is equal to theta. This type of algebraic manipulation and going back and forth between trigonometric functions and their inverses is going to be incredibly useful when it comes to solving different trigonometric equations, and in particular also not just in Calculus 1 but in Calculus 2 when it comes to trigonometric integration. Let's next take a look at how we can apply inverse trig functions and their basic inverse laws that are just defining properties of inverse functions to solve various equations or various problems. First of all, let's take a look at this little triangle. So we're asked to find theta in this triangle. From the triangle trigonometry, we know that I am now trying to look at the triangle from the perspective of the angle theta. So I'm trying to think of what function involves the adjacent and the hypotenuse. And that, of course, is cosine. So I can say that cosine of theta in this case is adjacent over hypotenuse, so 9 over 12. Or if I want to simplify, this is the same as saying that this is 3 over 4, dividing everything by 3. So now I have the expression that cosine of theta is 3/4, and as per our practice on the previous page, this is the same as saying that theta is inverse cosine of 3 over 4. Okay, this is the expression that you can plug into your calculator and actually calculate. We're only talking about a triangle here, not all possible values of theta that satisfy this equation. So whatever unique answer your calculator gives you is, of course, the unique angle measurement that will match this triangle. So in degrees, the answer here will be 41 degrees. Of course, there are other ways to solve this triangle. For example, we have the lengths of these two sides, which will allow us to calculate the length of the third side as 12 squared minus 9 squared, all square root. And then, once we have all three sides available to us, we don't have to use cosine. We can use any other trigonometric function, such as sine, tangent, and whatnot. Now, the basic trigonometric inverse laws talk about the fact that sine and inverse sine are inverse functions of each other, so in a sense they should cancel each other's actions and produce the original input back, except for we have to make sure that we follow the restrictions on the domain that we originally imposed in order for the sine inverse to exist in the first place. So let's take a look at x and work our way inside out through sine inverse and then sine in this case. First of all, x has to go into sine inverse, so we have to be able to evaluate this value here. Now recall that the domain for sine inverse is between -1 and 1. Once I have that, I can calculate the sine of just about anything. So as long as my x is between -1 and 1, we are good to go. Notice that in this case, if x is not in this domain, then the answer will not exist at all. For the next one here, I first have to apply the function of sine onto my x. So we have to recall that, originally I can plug this I can plug any x into here, but then once I evaluate this, my expression has to go into sine inverse, who has a restricted domain. Let me make a note here. Restricted domain of negative pi over 2 to pi over 2, right? And so I have to be able to then plug this in, which means that this expression will only be equal to my original angle if I am in the restricted domain to begin with. So this will be true only for x is between negative pi over 2 and pi over 2. So an important distinction to note here is that in this case, this sine of sine inverse of x is equal to x if x is in between negative 1 and 1, or it does not exist at all. Whereas in the second expression, sine inverse of sine x is equal to x if x is between these two values, or it will exist but might not equal to x. It will equal to some other angle from the unrestricted domain, or it won't equal to x. Okay. Similarly, the logic can be applied to the expressions of cosine inverse of x and cosine inverse of cosine of x with the exact same type of results. So this will only be true between negative 1 and 1 or not exist otherwise. And this will be true for 0 to pi, or the angle might not be equal to x. For the tangent, we have that tan of tan inverse will always be true, whereas the restricted domain comes into place when we apply tangent first, but then have to evaluate tangent inverse. So our restricted domain there was between negative pi over 2 and pi over 2. With this in mind, let's now actually compute some various combinations of the inverse functions. So the first one here, sine of sine inverse of 1/2. So I notice that I have this form here, and it will be equal to x as long as my original x is between negative 1 and 1, which it is. So I can with no problem say that in this case, the sine and sine inverse cancel each other's actions to produce the original input. Let's take a look at this guy here. Sine inverse of sine of pi by 4. So I am in this case here, and it will be equal to x as long as my angle is between negative pi by 2 and pi by 2, which it is. So this also is the easy case where I simply get my number back. Let's take a look at this example now. So I have sine of sine inverse of 2. Again, I can take a look at this expression here. I will get my original angle as long as it's between negative 1 and 1, or notice that it does not exist otherwise. Here my number is not between negative 1 and 1, so my answer is simply does not exist. Let's try to see if we can analyze this or justify it out without relying on the actual identities. If I am starting computations from inside, first of all, I have to compute sine inverse of 2. So recall that sine inverse of 2 means I have to think of an angle whose sine is 2, which of course is not possible because sine of any angle is between negative 1 and 1, which is exactly where this restriction comes from. For this, again, let's try not to use the identities, but rather carry out the evaluations of on our own. So first of all, I have sine inverse of sine of 2 pi. So going from inside out, I have to compute sine of 2 pi. Now, sine of 2 pi is equal to 0. So then my next step, I have to compute sine inverse of 0. And thinking, this corresponds to thinking sine of what angle is 0, and I have to land in between negative pi and pi by 2 and pi by 2. This will be 0. Okay, so notice here that the answer does exist, it's equal to 0, but of course it's not the same as the angle that was originally plugged into the sine inverse and sine. Okay, so the answer exists, but it's not the same angle. We will see something very similar in this example here, where if you carry calculations through from the inside out, you will notice that tangent of 2, your calculator will give you a value of minus 2.18, and then calculating the tan inverse of that number will actually produce 2 minus pi. Okay, so the answer does exist, but it's not equal to the original angle that you've provided. You're provided inside the two functions here. In more generality, so this is the basic inverse rules work with the same function and its inverse applied back to back in whatever order. What if I have functions that are not of the same nature? One is the inverse, but not of the exact same function as I have. So sine, but cosine inverse, not sine inverse. Okay, there's a number of ways of doing this, and we will go through two different ones for two of these different examples. Okay, so the one thing I can think of right away is this cosine inverse of 3/2 is an angle measure of some angle theta. And so what I'm after now is this sine of theta, where theta is this angle that I don't know the actual exact measurement for. Now, one thing that you can do is construct yourself a little triangle here. So I have a triangle, and I can decide to call some angle theta, just not the right angle. So let's say my theta will be this guy right here. So notice that what I know is that the cosine inverse of 3/2 is theta. Let me write this out. Cosine inverse of 3/2 is theta, which means taking advantage of our practice of going back and forth between trig and inverse trig functions, this is the same as saying that cosine of theta is 3/5. Now, cosine in a triangle, in a right angle triangle, is adjacent over hypotenuse. So I can simply label my adjacent side as the length of 3 and my hypotenuse, as the length of 5 here. Now notice that what I actually want is the sine of this angle. So I can simply write that out. Sine of theta is of course going to be opposite over hypotenuse. Let me write this out. And so now I simply have to calculate the values of the lengths of those two sides. I don't have the length for the opposite here, but I'm in the right angle triangle, so I can simply apply Pythagoras Theorem or recognize that this is a very familiar 3, 4, 5 triangle. So the length of this side has to be 4, which again you can calculate as 5 squared minus 3 squared. Okay, so my opposite is now of length 4, and my hypotenuse is of length 5. So my sine of theta, which is the thing that I was trying to compute in the first place, is 4/5. So my final answer here is 4/5. Drawing a simple triangle is a very, very powerful tool in this case. For the second one, instead of drawing a triangle, I am going to use various trigonometric identities to actually get at the answer. You can always try to draw a triangle. This is simply another way to go. Okay, so I'm going to label whatever is inside here, again, with some kind of variable. So I use theta here, let me use something else here, let's call it y. So sine inverse of x is going to be y. Let me write this out on the side here. Sine inverse of x is y. And what I'm after now is tangent of y, right? Tangent of y. This whole thing inside is now called y. What I know is sine inverse of x is y, and again, I can rewrite this in terms of non-inverse trigonometric functions as sine of y is equal to x. Well, this is good news because I now know what sine of y is, it's x. What I want to know is tangent. Now I know that tangent is sine over cosine, so let me write this out here. This is sine of y over cosine of y, and I already know that sine of y is x. So I have that it's x over cosine of y. So now all I need to figure out is what is cosine of y equal to in terms of x. What is the relationship between sine and cosine? Well, that's the basic trigonometric identity, right? So I have that cosine squared y plus sine squared y is equal to 1 for any angle measure y, and I am after the value of cosine. So solving this for cosine of y, I'm going to get plus or minus square root of 1 minus sine squared y. Now I have to decide which square root am I going to take? The positive one or the negative one? Now remember that this all comes from, for the angle y, as the value of the inverse sine. Now recall that this was restricted to be in between negative pi by 2 and pi by 2 on the unit circle. So let me throw a picture of a unit circle up here really quick. So I am looking in between these two quadrants, and in both of these quadrants the cosine value is positive because the cosine value is the x value of the points on the circle, and all of these points have a positive x coordinate, which means that cosine is going to be the positive on both of those quadrants. So it's the positive square root that I'm after, and I can of course replace my sine of y with the x that it's equal to. So here I have 1 minus x squared, and this is the value for my cosine. So now I can go all the way back up here to plug that in. So I have x over square root of 1 minus x squared. And this will be my final answer as the simplification for this expression. So in terms of x, notice that in the final answer, I only have x's, I don't have any trig functions. So no matter what angle x you give me now, I will be able to evaluate this by simply plugging this into here. Please take a look at Module 6C on WebWork to practice the basics of various inverse trigonometric functions before we get into solving trigonometric equations in the next section.